Now we'll talk about isolation and multi-version concurrency control. We will see what it is. We'll talk about snapshots and how isolation levels are implemented in Postgres. We'll talk about locking and about vacuum. What is MVCC, multi-version concurrency control? When you have several concurrently running transactions which are working with the same data, you must do something with it. If you will not use anything, will not do anything, it will be absolutely chaos, because one transaction changes data and other reads this data in some intermediate state, and you get data which is not consistent. So it is bad solution. What else? You can lock everything and just execute your transactions one by one sequentially. It will get you full isolation, but performance will suffer because you cannot run several transactions at one time. It is also bad for the database. So you have something to do to run. On one hand, you must execute transactions simultaneously, and on the other hand, you have to ensure isolation. When two different transactions read the same data, it's okay. When two transactions change the same data, it's also a simple situation, because we cannot allow two transactions to change it simultaneously. So one transaction changing data and locking it, and another just have to wait for a lock. And what if one transaction is changing data and other wants to read this data? It's more interesting situation. You also can lock data, but it's not very good for performance reasons. So Postgres, and as far as I know, most high-performance databases today uses multi-version protocol. Idea is that your data can exist in database in different states. You have different versions of the same data. So one transaction can change its own version, and other transaction can read its version, and they don't intersect and don't and you have no problems here. What version is? For example, we have one row, this one picture. When you insert this row, it creates the first version of this row. When you change data by update statement, you create another version of the same data. Then you can update it again, and so on. And in the end of life cycle, you delete this row, and it exists no more. So we have several versions, and to distinguish these versions, we must know its start time and end time. Postgres doesn't use timestamps for that. It uses transaction identifiers. Transaction identifiers and Postgres are sequentially increasing. So we can use it as like tick counter. So we store, with each row version, we store two numbers. Transaction ID which creates this version and transaction ID which makes this version obsolete. And using these numbers we can distinguish row versions and choose row versions we need. How we do this? We use what is called data snapshots. When you execute a statement, it must construct its snapshot which contains consistent data as of some time when you run this query. Here it is shown by dashed vertical line here. And we must choose one version of each row. No more than one version. For example, for row 1, we have two versions. And at the moment when we create snapshot, the second version was actual version, so it gets into our snapshot.
Snapshot, who makes the snapshot? The reading process? Who makes the snapshot?
Any statement which must access data. So any SQL command: select, update, delete, insert, so on.
For example,
yeah.
If I update any row, there is no necessity to make snapshot from the previous state because nobody reads them. Only if somebody began to read, maybe there is a necessity of the snapshot.
Snapshot is created always.
Until you, in any state, you need to delete them.
We will talk about it.
Okay.
For second row, you can see three row versions here. At the moment when we create snapshot, the second row version was actual, so it gets into our snapshot. And after that, this row may be changed, may be deleted, but as long as you create your snapshot, you will see this row version, no matter what happened after that. So that's why we can mix reads and writes. If I read this row version, other commands may change this row, but I still will see the same row version as it was before.
A snapshot, in other words, is the highest transaction ID of all the relevant data. Is it right?
Physically, snapshot is several numbers. One of them is transaction ID.
The highest?
No, it's transaction ID, current transaction ID at the moment when we create snapshot. It defines position of this line.
Yes, but it refers to the data with the highest transaction ID.
At the moment when
it was changed.
It was created, snapshot was created. And also we must have a list of active transactions at the moment when we create our snapshot. We must have this list because we don't want to see data of transactions that were active and were not committed at the moment when we create our snapshot. So we have a list of these transactions. So basically it's several numbers. It's not a physical copy of raw versions, of course, just several numbers. So creating snapshot is not a hard procedure. It's very quick. It's no problem at all. And row number 3 didn't get into our snapshot because it was deleted before we created the snapshot. That's it. What benefits multi-version concurrency control gives us? We can deal with absolute minimum of locking. We lock one transaction can block another transaction just in one case, when both transactions are trying to change the same row. Reading never blocks other reading transaction and never blocks changing transaction, writing transactions. And writing transaction never blocks reading. So a lot of transactions can run on the same data simultaneously.
What is the default, a row lock or page lock or block lock? What is the default of reading, for example? It's a row lock?
Row lock.
Or, for example, in SQL server, it's on the level of the page. So it's
Postgres uses row level locking, and it never escalates these locks because it is very cheap for him. It doesn't store locks in operating memory. Locks are in data pages itself. So you can lock millions of rows and it is okay to Postgres. But in addition to row locking, we of course have locks on higher levels. For example, on table level, because you don't want that someone deletes table which you are selecting, for example, or if you creating an index, you cannot change contents of your table and so on. But these high-level locks are usually not a problem because it is preventing situations which are not common. You don't often delete tables, for example. So, you have a question?
Yeah. Why do we need logs while it's we've got snapshots? Because snapshot is a, as I understand, is a different subset. Is a subset of the data in the current time. So why we need a log? We can delete a row in a one position of time and delete a row in another version of it. So why do we need a log?
We need logs because we cannot change the same row concurrently.
Yeah, that I understand.
Yeah, and that the only log is used in this situation.
Yeah, but if you make a transaction as a client, make a transaction, in the same time I am as a client making a transaction to the same rows, to the same data. You have got your own snapshot, and I've got my snapshot, right?
Yes, that's right.
So why can we go both ways? Like, why do you need a lock in this situation?
Row level lock, you mean?
For example, for updates.
If you write if you read data, your transaction read data, and my transaction is changing this data, no locks are required. We can do it simultaneously. The only situation when we use locking is when your transaction changes some row and my transaction tries to change the same row. And we cannot do it concurrently, because I cannot change some historical version of row. I must change actual data. Otherwise, one transaction can, it is called lost updates, lost changes. You change something and I override them and you lost your changes. And it's not what you expect from transactions. So the only situation when locking is used is when we update the same row in the same time. Locks usually acquired automatically, and you don't think about them, and they released when you commit or roll back your transaction. But if you use isolation levels less strict than serializable, sometimes you have to lock some objects manually to prevent some anomalies. You can also do it. There are commands like select for update or lock table and so on. Sometimes you need to do it. For multi-version concurrency control to work, we need to know states of each transaction in database. State of transaction, status of transactions is stored in a special structure which is called exact. In Postgres before Postgres 10, it was called clog or commit log. But it was some database administrators when Postgres is run out of space, look into directories and see, oh, clog. Logs, it's something that I can delete, and they delete this directory and Postgres stops to function after that. So in Postgres 10, this directory was renamed to exact to show that it is very important part of data. Basically, it files where you have 2 bits per each transaction. 1 bit is committed and another bit is aborted. So either transaction is not committed and not aborted, so it is running transaction, or you have one of these 2 bits set, and it shows the state of the transaction. To commit transaction, you just have to set commit bit for transaction. That's all. So commit is very quick process. You don't have to write anything instead of write a head log, but it's another story. And the same is true for rollbacks. To roll back your transaction, you just need to set rollback bit, and that's all. We don't physically rolling back changes that your transaction made, just setting 1 bit.
So
Another transactions.
Rollback has to be very quick also.
Yeah,
Rollback has to be
rollback
very
is as quick as commit in Postgres. it's a matter of visibility rules. When other transaction is creating its snapshot, it will see that here we have raw version, but it was created by rollback transactions, so I don't have, I cannot see this raw version, and another raw version will get into the snapshot. It works very efficient, very perfect, but there is one point. In course of time, in your tables, you get all historical raw versions. They are stored in the same data file as current raw versions. So you have all history of your changes. That's why files are bloating, they increase in size, and at some moment, at some point, you have to physically delete historical raw versions to free up some space to use for subsequent changes or inserts. And this is the job of vacuum process. Vacuum finds raw versions that are no longer needed, which are not present in any open snapshot, and it deletes this version and free up some space.
Yeah, what is the rule of cleaning process? How it's do it? I can do it manually, or it's full automatic?
Yeah, both ways, in fact. We have so-called auto vacuum, which is a process like a daemon, which automatically vacuums all data. And if you want, you can run this command manually. Just type vacuum and table name, and it will vacuum it. It's like vacuum cleaner. So in your data pages, you will have some like holes which you can use, which Postgres can use for new raw versions. Usually you have some data, some file. It will grow a bit because of historical data. After that you run vacuum. It deletes some raw versions. And after that, Postgres uses this free space inside this file. So file will be bigger than it is in the beginning of work, but it must not grow constantly. But sometimes there may be a situation when vacuum can't clean up your table in time. For example, you have many big tables, you have not configured auto vacuum right way, and so on. So your files may grow very large. If that happens, you may run vacuum full. This command locks your table exclusively and reconstructs it from scratch. So you get small files, but when vacuum full is working, you cannot do anything with table, including selects. So it is not so good command for production environment. Fortunately, we have third-party tools like pgRepack or pgSqueeze, which can compact your files, and they also requires exclusive log, but on some very short period of time. Yeah, and about auto vacuum, it's background process. You can see auto vacuum launcher process. It schedules work and runs auto vacuum worker processes to do the cleaning. It is preferred way. You just need to configure your auto vacuum in correct way, and after that hopefully it will work smoothly. Okay, and a couple of words about isolation levels. SQL standard defines 4 isolation levels. Less strict is read uncommitted, which allows you to read the data that were changed but not committed yet. It is not supported by Postgres because it's in times when SQL standard was developed, I believe it was SQL 92 standard. Most databases were using locking, and it was believed that higher isolation level, the more locks you must have on your rows and tables. So standard defined these levels to allow faster work on less strict isolation levels. But Postgres, thanks to multi-version concurrency control, can work on read committed level as fast as it would work on read uncommitted level. So you just don't need read uncommitted because it's no benefit from it. Read committed is the default level for Postgres. On this level, each SQL command builds its own data snapshot when it runs, when it begins to run. Yeah.
If I select the whole data table,
yeah,
the big data table,
yeah,
okay? So it actually creates the whole snapshot of the whole table.
Snapshot is not physical copy of data; it's just several numbers. So it's quick process, no matter how many data you will need.
10 million rows?
It doesn't depend on number of rows. When you create snapshot, you don't know how many rows you will need. You just remember current transaction ID and list of open transaction IDs. That's all. This information is enough to understand which row version must be in your snapshot.
For each row, actually?
Yeah, yeah. So no matter how many data you process. So each SQL command works with its own snapshot. This means this command sees only committed data, and in the state when our command begins to work. So you can write select, which requires several hours to work, and it will see the same data.
It will see the data at the beginning of transaction
Or beginning
of statement.
of statement. And another level is repeatable read. On this level, each command in transaction use the same snapshot. So the first command in transaction creates snapshot, and other commands use the same snapshot. So on this level, you can write several selects, and they will see the same data. It is useful, for example, for reports, which consists of several selects, which must see consistent data. And the last isolation level is serializable. On serializable level, your transaction works as though it is working alone in the database. So if your transaction is correct alone, it will be correct in any concurrent execution. So on this level, you cannot think about isolation at all, just write code as so as you work alone. And Postgres supports this level. There are some limitations. For example, you cannot run serializable queries on replicas and some other limitations. But this level also works. Okay, let's see a little demonstration. Okay. I cannot see last lines on my laptop. That's why I Three. Okay. In this demonstration, we will see that indeed there can be several versions of the same row in database. So you can see it. Let's create a table and insert one row in it. It is our first version. Now we start transaction. It's begin command. We can look at transaction ID, txid current function. I have this number here. And we can look into the table, and obviously we will see the first version because it's the only version that we have in table yet. Here I show two additional columns. They are hidden columns, so select star will not show them, but you can name them. Name these columns xmin and xmax. This is two points. One is number of transactions that created this row version, and xmax is number of transactions that deleted this row version.
But it's not the same transaction ID.
No.
This is the 69 and the...
Yes, because this row version was created in previous transaction. this insert, it was previous transaction, it had number 69. And now we started another transaction, which is 70. And we see here that this row version was created by transaction 69.
But you didn't commit.
Yeah. PSQL uses auto commit. If you didn't write begin, each command executes in its own transaction and automatically commits. So here create table is one transaction, insert is another transaction, and here I start transaction with begin, and after that I will have to either commit it or roll back. Okay, this 0 xmax is 0. It means that this row version is current row version and no one deletes it yet. Now we'll start another transaction. It is denoted by vertical bars. If you want to reproduce it, you can open another terminal, start PSQL, and run these commands in another terminal. We start another transaction. It is number 71. And of course, it sees the same row version because it is the only row version. Now, let's change our row. We can write this update command. This will be second version. And transaction which changes data, it sees its own changes. So my transaction see a second version, and xmin is 71. The question is, what will see the first transaction? What do you think?
Last value, because it do commit. The first value 70.
70.
Yeah, because
First row version.
Yeah, because you did commit.
Yeah, exactly. I perform update, but I didn't commit. So the first transaction will see the first version. So we have two row versions that are existing, and we have one transaction that see one row version and another transaction that see other row version.
You said that there is an auto commit.
Yeah.
You don't start
Yes.
begin.
Yes.
So the update committed.
No. Because I started transaction by begin here. Look at xmarks field. We can see, despite of all isolation, that some other transaction already makes this row version absolute. And we can see its identifier here. But still, we see the first version. And now the second transaction commit its changes. And what will the first transaction see after that? It will see the second version because it is committed. And we have read committed isolation level. As soon as other transaction committed data, the next SQL command will see these changes. So we see as the second version. And first version is no longer needed. We have no transaction that can see the first version, and subsequent transactions also cannot see it. So the first row version can be vacuumed, and if you run vacuum at this point, it will clean this row version. What about logs? Let's do the same, but now our two transactions will try to update the same row. First transaction, begin. We update our row for third version. And second transaction tries to update the same row. If you do this command, you will see that the second update just hangs up and nothing happens. That's because it is blocked by the first transaction. As soon as first transaction will commit or roll back its changes, the second transaction can go on. For example, we commit our change, and the second transaction can do its own update after that. So this is how it works. Any questions? Okay. Let's do the practice. It is intended for work with different isolation levels. You can see how it differs one from another.